opportunity to be able to present the first CIBSE Yen London seminar, and also how exciting for whoever's lucky enough to be able to present for everyone beyond me, because this level of attendance is brilliant. What an awesome community we're all a part of. My name will be plastered all over this presentation. My contact details are also going to be at the end. If anything comes up, or if you have any follow-on questions, just get in touch. If it's about the presentation, it's about Lochinvar, it's about Yen London, it's about any of those things, I'm here to help, and so are my committee members as well. So, well, I say my committee members, I don't run it, Erato does, so she'll be around in a bit. But yeah, I'm going to get cracking with the actual seminar. So the topic of today's presentation, pretty topical, which is probably why it reflects the numbers: commercial heat pumps for heating and hot water applications. So I'm just going to introduce my company very quickly, just before we get started. I think it's just important to do that so we know where what I'm talking about sort of sits. My company manufactures water heaters, boilers and heat pumps, but the range is always 40 kilowatts through to 500 kilowatts on a single unit. So we're talking about a single unit being that sort of size. 4 of those would be a couple megawatts worth of systems. So when we look at schematics in a bit, how heat pumps work, how they talk, how they operate, how they help service your buildings, we're talking about that light commercial through to sort of light industrial space. So just bear that in mind, because if you work on domestic resi, the principles are but it's different, and there'll be a few things which are different. Same for heavy industrial, it's going to be different. This is that light to heavy commercial sort of space. Okay, so first thing to talk about, very recently we've had this sudden surge in popularity for heat pump technologies. A lot of that is down to the fact that the grid electrical infrastructure for the country is definitely getting greener. So much so that the most recent level rendition of SAP 10, which will be residential building regs, has stated that electricity in terms of emissions, kilograms of CO2 per kilowatt hour, is pretty much on par with gas burning energy sources now. So if you've got a gas boiler or an electric immersion heater servicing a building, from a carbon emission rate, it's going to have a very, very similar impact. Now, the fact that gas is a third of the price of electric, obviously you wouldn't be going for an electric only sort of heating system in that format, but from a carbon point of view, they're pretty much bang for buck. Historically, gas was actually considered 2.5 times cleaner than electric, which is a bit of a surprising stat, but probably because historically as well, our electrical infrastructure for the country has been supported by coal burning power plants, which, you know, when you have a low efficiency source like that, generating all of our electric, you can see dirty. But now, take an electric air source heat pump or water source heat pump or any heat pump renewable technology like that, if you apply it to an application and it's working with an efficiency of, let's say, 300%, well, a 300% system would be like, what, a third of the equivalent running emissions of a gas product? So you can see why, straight away, if you integrate an air source heat pump into a new building or an existing building, whatever it is, the carbon impact is massive. So that's why air source heat pumps getting more and more popular. Part L2A is out to consultation. If it's not already come back or gone out, it will be getting updated very soon anyway. Chances are when it's updated, the Part L, which is your commercial building reg, will be updated with these emission factors or very similar emission factors. So yeah, watch this space, because heat pumps are busy at the moment, very popular, and it's going to get more and more so. There's other things coming out as well. You've probably seen the Public Sector Decarbonisation Fund. Well, there's £1 billion set aside by the UK government to be owned by local authorities. Heat pumps are just going to keep going one way, almost certainly. The other thing is as well with this sort of technology, it's now become quite cool to be green. So yeah, I mean, you've got Greta Thunberg leading marches in Bristol with massive attendance, and it's just become very mainstream. So people want to be seen to be green. I mean, I work for a manufacturer. We manufacture solar panels as well, and I get quite a lot of inquiries for people who have got a small building and they want a solar panel on it. And the actual carbon offset that solar panel would get for a single panel is probably very minimal. But people quite like the idea of it, because if you put a 45-degree solar panel on a roof, you've created a green flag. It's a green building, and it's got some green credentials. It's an attractive, popular thing. So yeah, there's definitely an end user awareness now as well, which we've never had historically. So it's great that it's still going that way. And the other thing is air source heat pumps. When you're using an air source heat pump, Europe is broken down into 3 individual climate zones. You've got your cold climate zone, like Norwegian countries, Eastern Europe, really landlocked areas, the places which typically you'd associate with a cooler climate. You've got your average climate zone, which is your more middle blue, I suppose, different shade, sort of the middle shade of blue here. North of the UK, average climate zone, most of France, average climate zone, north of Italy, average climate zone. And then you've got your warmer climate zone. So if you're lucky enough to be in the south of the UK, you are in a climate zone, an air source heat pump would be considering to be comparable to the outskirts of Spain. So not necessarily got the nice holiday weather, but what we have got is a very stable climate. We don't get big peaks and troughs in terms of outside air temperature. We're actually really steady, and the impact of that is Ireland, south of the UK, just under East Anglia, so London, you're in there. Great place to install an electric heat pump in terms of its seasonal efficiency. So when you look at an air source heat pump, water source heat pump, any type of heat pump, there will be a SCOP figure given. So you've got COP, which is coefficient of performance at a specific point in time. Then you've got SCOP, which is seasonal coefficient of performance, because its efficiency is going to be dictated by the climate it's working in. So swings. Okay, so very quick introduction. I'm sure a lot of that you were already aware of, but it's just nice to sort of recap on the reasons why heat pumps are now so popular. They're already popular, they're already cool, they already worked very effectively, there was renewable heat incentives, but now as the grid gets cleaner, the heat pumps' carbon credentials get stronger and stronger. The other thing is as well, which I suppose is worth mentioning, at this point in time, electric and gas are comparable in terms of emission rate, sort of bang for buck. So if you put in that heat pump, you know, I said third of the equivalent running emissions, which sounds great. But in 10 years' time, when the grid is cleaner again, the gas product's carbon rate just is what it is. Gas doesn't get cleaner. The only thing that can get cleaner about gas is that the pumping stations that pump it around that are electric are now slightly more efficient because the grid's cleaner. So whereas with electric, as the grid continues to get greener, the carbon reduction impact for that building going forward, it gets exponentially better. So yeah, that's why heat pumps are popular, and this is going to be the section on how we use them. Now, I am aware a few people have joined since I started, so I'm just going to say again quickly, thank you all so much for attending first CIBSE Yen London seminar that we've had the privilege of hosting, and luckily, well, and I'm lucky enough to be able to host the first one as a committee member and CPD provider. Okay, heating applications for electric air source heat pumps. So the first section of this seminar, yeah, we've just done why. We're about to do how we use them. This is focused on air source heat pumps. The next bit we're going to go on to is going to be more based on sort of retrofits and existing building stock, making them cleaner. So this is the section we're thinking about for maybe new builds and buildings we're going into the process of designing or doing full building refurbishments on. Okay, so what we have on the screen at the moment is a graph, and what we have along the bottom of that graph is an outside air temperature. So this is obviously the condition that the air source heat pump is going to be operating in. The air source heat pump is going to be external plant. The range it will work in is greater than this, but typically they'll work down to -20. The graph just happens to be plotted up to +20, so that's our outside air temperature. Up through the middle, we've got the kilowatt rating of the electric air source heat pump. And this is what I would call a 45 kilowatt air source heat pump. And it is 45 kilowatts when our outside air temperature is 7 degrees centigrade. Any time other than that, the kilowatt rating is different to the 45. But we would state it's 45 kilowatts because that's what the standard EN test figure or European test figure for comparing products is benchmarked on. So if you were to look at any manufacturer's air source heat pump, the data will be published as standard at 7 degrees centigrade outside air temperature. That's the outside air temperature that apparently is our average in the UK. So for that reason, 45 kilowatt heat pump, but it is only really as good as whatever our design air temperature is. So you're in the city of London, chances are you're going to be designing to -2. If you're somewhere more rural, maybe you're coming in from East Anglia or something, you might be designing to -4 if that's where the site is. The green line that's just appeared on the screen the load. So that's the nicely selected, sort of appropriately sized air source heat pump. But remember, I called it a 45 kilowatt unit. Well, it's only actually the kilowatt rating that you would require at your design temperature. So that's why whenever you approach a manufacturer for a quotation, because you're looking at designing a building, if you're a mechanical engineer or you're getting efficiencies or whatever it may be, chances are the heat pump looks over-spec'd until you actually look at what it's capable of at our design condition. Always bear that in mind. And just before I go on to the next slide, I always like to point this bit out as well. Between an outside air temperature of 4 degrees and 2 degrees centigrade, we get this sudden drop off in the performance of the heat pump. I mean, we've got quite a big crowd, so I'm not going to open it up to the floor. Yeah, usually I would, but no, we've got a great attendance. But the reason for this drop off in terms of performance is because it's the first time the refrigerant inside an electric air source heat pump is going to be below freezing. But it's not that cold outside that there's not that much humidity. So quite a humid atmosphere, going over an evaporator grill, it starts to form an ice layer on the heat pump. And when you get that ice layer on the heat pump, what happens is, even though the fans are spinning, drawing air from outside across our evaporator to take in that ambient heat, outside air that it's working in, those ice deposits restrict the airflow. And when they restrict the airflow, they affect its performance. And when they affect its performance too much, what it will do is it will go into a defrost function to get the frost off the evaporator so it can start operating efficiently again. So that's why between 4 and 2 degrees, we get this sudden drop off in performance. When we get beyond 2 degrees, I mean, yeah, it's cold outside, but there's just not that much humidity. So any ice that forms on your evaporator is going to be a very fine layer. It's not going to mess up your airflow. The heat pump's going to continue to function effectively. So yeah, if you have a heat pump that's going to spend most of its life between 4 and 2 degrees centigrade, it's not going to have a very good time. So when we take a heat pump and apply it to a heating system, air source heat pump, thermal store, and then ancillaries. Very important. Every single item of that is important and will pretty much always be the case. So what happens is your air source heat pump monitors a sensor, and that sensor's inside a thermal store. So when you've worked with heating systems in the past, you've probably had a boiler with a low loss header. We have to have a thermal store with heat pumps because they work very differently. The heat pump is going to be using compressors. So what we do with compressors, they have a big current draw to turn them on. And then to make them run efficiently, you want them to run for a long period of time. So you want to turn it on and keep it running. You can't do that with a system which has a low content, unless you've somehow perfectly matched your loadings. But that's pretty much impossible because the heat pump performance changes as the outside air temperature changes. So we have a thermal store, and that's going to be anything from 10 to 20 litres per kilowatt of air source heat pump, as a rule of thumb. So if I've got a 45 kilowatt heat pump, I'm going to have a 400 litre thermal store. I'm going to say there's 50 litres of water in our pipe, so no worries. And the heat pump is going to monitor a sensor and maintain a temperature in that tank. The heat pump's going to flow. If we've got a target temperature of 45 degrees, it's a low temperature circuit we're serving, probably radiators. But to achieve that, what the heat pump will do is it will flow at 47 degrees and it will return at 42. The heat pump is going to work on a 5-degree delta T. So if you've worked with gas boilers in the past, they're going to work on a 20. They're working at 80, 60, right? Well, this can only work on a 5-degree delta T. It's a much faster flow rate. So a 45 kilowatt boiler with a 20-degree delta T would require a quarter of the flow rate a heat pump would require because it's got that tighter delta T. So for the same heat transfer, you need to flow 4 times faster. 4 times the flow rate means a massive increase in your velocity, and the impact of that is you're going to want to be increasing your pipe work sizing. So just bear that in mind as well. 5-degree delta T means much higher flow rate. Much higher flow rate means bigger bore pipe work, because otherwise your velocity is going to get too high. It's going to scrub the inside of the copper pipes out, leads to premature failures. So we've got a 45 kilowatt heat pump serving our 400 litre thermal store. we're flowing in at 47 degrees, we're returning at 42 degrees, 5 degrees on the primary. The secondary side of the system would be independent, operating just in the same way a heating system would be if it was the secondary side of a low loss header instead of thermal store. The water is going to go to our various zones, do whatever it needs to do to heat up that building to satisfy the various loads and various zones in that building and keep the occupier warm and happy. So that is a basic application for an air source heat pump. What do I say basic application? If you were to take that schematic and put it into a heating system with a secondary side designed, it would function very effectively.
Scott, just can we ask questions?
Oh yeah, of course. Yeah, sorry, I should have said yeah. I mean, there's a lot of people, so I'll field a couple questions. Definitely, yeah.
Real quick
totally
one.
Fine. Yeah, go for it.
If I was going to throw a heat exchanger in there on the secondary side to protect, let's say we're trying to retrofit a heat pump into an existing radiator system.
Asking for a friend.
Yeah. I throw a heat exchanger in there. Obviously, keep the buffer vessel on the left. Is there any other particular things we should be concerned about or cognizant of?
Retrofit heating system in that format. Keep in mind what you've just said. We're going to go on to hot water in just a minute. With hot water, what we do is we serve the plate prior to the buffer, but the buffer's usually a potable volume. But for you, if you were serving the plate to then do the heating, you wouldn't be serving a potable volume. So it's still going to work, but just ignore the hot water flow and cold feed. What you'll have is a heat pump serving a plate, pump on the secondary side, taking away all that energy, but your two pumps always operate at the same time. So the heat pump doesn't care, the buffer would be on the system side, and then that means that you'll flow out to your system much less restrictively than if you had a plate on the way back. Main reason I suppose you would do that is because if you put the plate on the secondary side of the thermal store, any flakes or debris block it up very quickly and you're going to have a lot of maintenance and downtime. Whereas if you have the buffer in between the dirty system and the plate, a lot of that sediment will sit at the base. But you'll see that in just a sec on a hot water schematic, but think of it from a heating point of view. Okay.
Thank you.
Cool. Okay, so the heating schematic we just looked at, this is an application basically doing exactly the same thing as we've just described. What we've got is the heat pump, and its job in life is to maintain a buffer vessel at 50 degrees. This is a case study. It's called the Cali White Care Home. It's on Lochinvar's website. Check it out if you like, but it's a heat pump working in tandem with a couple boilers. So heat pump serves a thermal store, maintains it at 50. We get a flow off to our building, goes off to the residents' care home, and it heats up their room to whatever their desired set point temperature is. The heat pump is capable of working to an outside air temperature of about 7 degrees in this application, because that's what gave them the equivalent carbon offset they needed from a hot water point of view, from a planning application point of view. And then what happens is, typically, because it's a care home, someone turns up the room thermostat, increasing the kilowatt loading on the building because your outside air temperature and your building temperature, big disparity in terms of the temperatures there all of a sudden. So the impact is the kilowatt load goes up to maintain the building at temperature. Gas boiler will recognise that the thermal store, well, actually the heat pump will recognise that the thermal store should be at 50, but it's now 49, it's now 47, it's now 46 degrees centigrade. It's working at 100% rate. We're taking out more energy than we're putting in. So what the boiler does is it turns on. It will be one of our, I think this is one of our CPM boilers, so 10-to-1 turn down ratio. It'll put 6 kilowatts in the system to basically top up to make sure that the user's satisfied, but it won't dominate the load, and that's the key. You never want to end up with a situation where the gas product dominates the load. You almost want the heat pump in a hybrid style system to be working as like the base load product. And then when the outside air temperature gets beyond 7 degrees for this building, the air source heat pump's never going to turn off. It'll work at 100% rate forever, and the gas boiler is just going to do your extreme peaks and troughs. So that's a hybrid style system. A lot of people like this approach as well because it gives you a massive reduction in your initial capital. If you've got a site that's got gas anyway, just for reference, a 60 kilowatt wall hung boiler would cost about £3,000. A 60 kilowatt air source heat pump plant cost would be about £25,000. So, you know, from a capital point of view, if you've got the ability to have your second point of failure as a gas product rather than a second heat pump, capital wise, it's going to make sense. Unless you've not got gas infrastructure on site, in which case digging a gas trench is pretty expensive. But, you know, these are the considerations you make as designers on application by application basis. Okay, So this is the same sort of story again, but this is going to be for hot water. I'm not going to labour this chart because it's just the same as the one before, same performance ratios. It's just that this time our loading is 26 kilowatts because that just happens to be what we need for a 2-hour heat up time on a 900 litre storage vessel. You just notice that that heat up curve, the green line, hot water is hot water. A 2-hour heat up time is a 2-hour heat up time, regardless of whether it's summer or winter. Okay, so when we're looking at air source heat pumps for hot water, it's quite an interesting one, really, because the industry originally, like, I mean, there's obviously the Yen network. There might be some people a bit more senior in here, but a long time ago, the industry had a long period of time, and you've probably seen it. You've probably seen summer boilers, you know, this sort of thing. And basically, what you had in plant rooms was you had a load of 3,000 litre clarifiers storing the peak of hot water, and they'd all have long heat up times on. And then what we did was we transitioned to what we've been working on probably for the last 5-6 years, which is a gas-fired water heater, which is a direct gas-fired water heater with 120 kilowatts of input or more, and a small storage volume, because that gets rid of our standing losses, and we can do it almost semi-instantaneously. And now we're working with heat pumps, and we're storing 10 to 20 litres per kilowatt of air source heat pump, remember? So now we're doing it with air source heat pumps. What we're doing is we're kind of doing that full loop and going back to the original idea where we store our peak and heat up over the long period of time. And the reasons we do that are twofold. So you've got the volume in the system to be able to defrost. You've got a volume in the system to keep the compressors running so they work effectively. Insulation standards are now significantly higher than ever before. So every storage vessel, like by default, is like C rated as a minimum. So the insulation depths are like upwards of 100 mil. So having these really well insulated vessels with low standing losses anyway gives us the ability to store more, downscale the size of the heat pump, reduce our initial capital investment, and get an overall system that runs more efficiently as a result, even though we've increased our standing losses with additional volume. So when you're working with an air source heat pump, at your design condition, when you're looking at hot water, you're looking for a 2-hour heat up time typically, unless it's healthcare and we're insistent that it's got to be a 1-hour heat up time, in which case that's perfectly acceptable, but you are going to lose some efficiency on the system, and you're going to increase the cost of the initial capex. Okay, so a hot water application or dirty heating system application. So for hot water, what we do, any public health engineer in here, I'm sure, will be wanting to see 60 degrees centigrade in their hot water vessel, which will be serving the building. To keep the efficiencies up, what we do is our heat pump flows at 63 degrees centigrade. Now, remember, we've got a 5-degree delta T, so we flow at 63, we return at 58. The plate heat exchanger is spec'd to only lose 1 degree across it. So what we end up with is these pretty substantial plate heat exchangers with big surface areas. And what that allows us to do is, even with a 5-degree delta T on the primary, on the secondary side, we flow out at 62. That 62 degrees centigrade will then flood the top 2/3 of this vessel, distribute off to the building at over 60. So our public health engineers are typically happy. Our building return comes back at 55. Flows into the base of the cylinder, blends with our cold feed as well if there's a demand on the building, floods through the plate heat exchanger again, circulates through, back at 62 degrees centigrade. So on this side of the system, we're at like 62, 58, something like that. That's not 5, is it? 62, 57. And on this side of the system, we're working 63, 58, so 1 degree higher than the secondary. This is the same principle you'd employ if you were doing a heat pump retrofitted onto a dirty system, and they were the sort of temperatures you were looking for. Except that would be your building flow, that would be your return, but there would be no outlets. Okay, and then it's just a case of making sure that that pump is spec'd to match the same flow as this pump here, and that way you know that you're putting into the plate exactly what you're getting out. Okay, so that was a hot water application. And now, very quickly, just to express the versatility of an air source heat pump and what they're capable of. I'm not going to labour this chart because it is even more of the same in terms of graphs, but from an application point of view, this is how you would address a heating and hot water challenge from an electric air source heat pump. So obviously different manufacturers' heat pumps will vary. I'm speaking for sort of Lochinvar's heat pump here, I suppose, because I have to, because that's the one I understand the controls on best. But what you get is 2 temperature sensors. You have a heating sensor, you have a hot water sensor. Under normal circumstances, your heat pump's job in life is schematic number one. It's to maintain a thermal store at a temperature so you can flow off to your various zones, serve a heating system, and satisfy the user and keep them warm on your nice cold winter's days. And then what it will do is it will auto monitor this BTS sensor, so the sanitary hot water sensor. And when it notices that that temperature has dropped below 60, it will switch alive from its control panel, turn a motorized pre-fault valve, increase its flow temperature to 63 degrees centigrade, flow into the plate heat exchanger at 63, return at 58. The secondary pump comes on briefly after that, taking our water back up to over 60 in the top 2/3 of this vessel to distribute off to the building. When it's satisfied that this vessel's now back up to 60, it will drop the live to the three-port valve, change its expectation on flow temperature, and go back to serving our heating system. So that's an example of how a heating and hot water application would work from a single air source heat pump. Now, that could, of course, be 4 air source heat pumps just in a reverse return format. You know, it depends on your load-ins, how many points of failure you want, how much resilience you want to build into the system. But yeah, these options are all there. Please bear in mind as well that, yes, my schematics do show immersion heaters, but those immersion heaters in any new build design will only ever come on if a heat pump breaks or it goes into a fault condition. So it's almost like your second point of failure, remember? So that second point of failure for resilience, an immersion heater at 60 kilowatts would probably cost 1,200 quid. The 60 kilowatt air source heat pump would cost 25 grand. So it's much from a residual, you know, peace of mind point of view, won't affect your carbon calculations because your carbon calculations are based on a full heat pump system. And the only time it will come on is if the actual heat pump goes into maintenance. Okay, so that's air source. We're now going to go on to water source, and the water source heat pump section. It's not going to take too long, but it just sort of shows how we've started using these in retrofit systems where it's very difficult to basically update your emitters. Okay. Okay, so a water source heat pump. This is the heating curve from a water source heat pump. At a 10-degree source temperature, we're looking at 35 kilowatts. At a 35-degree source temperature, we're looking at 70 kilowatts in the water source heat pump. Now, the interesting thing about this is that the input to that water source heat pump always stayed the same. Its absorption capabilities with that source temperature went up and up and up very quickly. So when you're looking at a source temperature of 35 degrees from a water source heat pump instead of 10, which would probably be like the source of a lake or a river or whatever, you're looking at efficiencies, electrical efficiencies of, I mean, I've got the value here. So flowing at 70 degrees centigrade, this heat pump will give you an efficiency of 540% if your source temperature is 35, which is massive. So what we do quite frequently on existing buildings where we don't want to mess about too much with the existing emitters, we have an air source heat pump serve a thermal storage vessel, and we take that thermal storage vessel up to 30 or 35 degrees. The water source heat pump will then take that 35 degrees from the thermal store. It doesn't care, it thinks it's a lake. It's not, it's a thermal store. It takes that 35 degrees and takes it up to any temperature you want, up to 80 degrees centigrade. So what we do is we run a compressor, we serve it at 35. So we've got a little system here working with an efficiency of say 400%. We've then got a water source heat pump using that energy, taking it up to say 75 degrees centigrade, which means we've now got a second system working with an efficiency of around 450%. We've drove 2 compressors. We've got 4.5 kilowatts out. So 2 in, 4.5 out. Total system efficiency on that sort of application would be about 230%. And that's 230%. Yeah, that's still less than half of the equivalent running CO2 figure that a gas-fired product would give you. So what we find is on a lot of retrofit applications, a lot of buildings like that, this sort of setup is quite favoured because what you end up with is a system that you can plug onto existing infrastructure, and you can work at these inflated flow temperatures, but still incredibly efficiently. It's not as high as you'd hope, you know. I mean, like a dedicated hot water system from a heat pump, I'd be looking at efficiency of about, the scope would be 3 to 3.2, so up to sort of 320%. A heating system at 50 degrees, you'd be looking at an efficiency of probably 350, 360%, which is massive. But that's assuming the building can accept a lower flow temperature. If the building can't accept that lower flow temperature and you need to flow at these inflated values to be able to utilize your existing emitters, if it's a retrofit, this is definitely a very easy, from an application point of view, way to go. If down the line you decided that you were going to upgrade your emitters so you didn't need the increased flow temperatures, absolutely fine, because all you'd do is turn down the temperature of this thermal store here. And if you turn down that temperature, what you do is you increase the overall efficiency again, because when you put compressors in series, it's doing the same equivalent work of one compressor not in series, which means that flowing at 60 degrees versus a heat pump flowing at 60 degrees, overall, your actual efficiency is going to be very comparable. So this is like a future-proof style design for an application where you can't flow at a low temperature yet, but you might do in the future. Or even if you don't in the future, it's still going to work. Same situation, but for hot water, except this would be, I mean, if you're doing it for hot water, chances are you're designing some kind of process plant, something like that. You know, you need really high hot water temperatures, but you need them efficiently. It might be like a bovine processing facility. So you need to spray it down with ridiculously hot sanitary hot water temperatures to make sure that you're cleaning everything down and disinfecting effectively. But by far our most popular schematic at the moment is definitely this one, shopping centres, whatever it may be. We have a thermal store, which will be at 35 degrees, typically served from an ambient loop. And that ambient loop will be a big one in a building, probably in a multi-functional style build. The water source heat pump can then pick up that 45 or 35 degrees, which is flowing around the building, go into a hot water system and turn it into a usable hot water application. Now, this is a really powerful tool because it allows you to tee into so many different things. I mean, if you've got a building with a load of waste, you've got a bit of server cabinets kicking out heat, and they're currently going to fans on a roof and it's ejecting to the atmosphere, don't eject it to the atmosphere, stick it into a thermal store if you can, because if you then pick that up with your water source heat pump, if you're using waste, you've created a hot water application with a genuine efficiency in excess of like 500%. Now that's massive. A fifth of the equivalent running emissions you would have with a gas-fired water heater. It's quite an impressive feat, definitely. So that's it for applications. Just going to go into where we sort of find these products most popular. Academic buildings. Generally, they were built in the 1960s. They've got big flat roofs, and if you want to create hot water, it's a really nice way to take emissions off-site when we're around kids. So you take the on-site emissions away. It then goes out into the countryside to a power plant or something. But on-site, you're left with electric air source heat pumps generating your hot water or heating. Office blocks. Now we've got the ability to flow at these sort of high temperatures still incredibly effectively for hot water. If you've got a big VRV or VRF system doing your heating and cooling for the building, it seems a shame really to hook it up to some gas infrastructure to run a system, because your capex on that gas infrastructure is probably more than the heat pumps, and you end up with a system which isn't as carbon friendly. So why would you not just stick a couple of additional heat pumps on the roof to do dedicated hot water, for example? You're in London, so you'll like this. I like this. Right, so I work in London a lot, pretty much all the time. We love air source heat pumps. We have no roof space or outside space, right? So any of the heat pumps that we supply can be upgraded, and this applies to anyone's heat pumps really, if they'll let you do it. Duct to the fanned outlet, put the unit inside. You can have air source heat pumps in an indoor environment if you've not got a suitable roof to mount them on. And what this does is, I mean, any plant room I've ever been in, it's the hottest room in a building. So this creates and simulates an environment where the air source heat pump is picking up air. If it's -4 outside, I guarantee it's not -4 in your plant room. This heat pump's going to work effectively all year round. But yeah, gyms and leisure facilities, definitely a good place for them. Resi blocks. So when you've got heat interface units demanding 70 degrees centigrade and a 40 return, that water source heat pump arrangement we looked at earlier allows us to flow at these inflated temperatures to service full electric only residences, which is fantastic. And yeah, it's just, there are endless number of projects in this sort of format now, high-end resi. And that pretty much concludes our seminar, to be honest. That's got us pretty much there. what I would ask everyone to do, and thank you very much for this, but if you could just fire through your details, because what we'll do is we'll send out feedback forms, but we'll also make sure you get your CPD certificates issued, so you get your CPD cert for attending the first London Yen seminar. Anyone who offers feedback as well, what I'm going to do is I'm going to incorporate you into a draw, which we'll do quickly off of the we'll do it off the Yen Instagram or something, and Lochinvar is going to give somebody a £50 Amazon voucher. So we're all probably quite junior in our career because we're the Young Engineers Network, so we're not making the big bucks yet. So someone will enjoy this for Christmas, I'm sure. So yeah, note that down. Please email me, smason@lochinvar.ltd.uk. Send through your details. We'll get you back a feedback form. We'll get you back your CPD certificate. We'll enter you into the draw. We'll do it from the Yen Instagram probably. If you're not already following the Yen Instagram, do. And that's it. Thank you very much for watching. Thank you all very much for coming along to today's seminar. And yeah, if anyone's got any questions at this point, now's probably the time, or wants to ask any questions relating to the committee or whatever it may be. But yeah, enjoy the rest of your day.
Scott, I have another question. And, someone else can go.
No problem, no problem. I'm just going to thank everybody. So if you have a question, just go for it, and I'll.
So yeah, I've got a project where we're trying to retrofit again, and we've got one block of the buildings which is running on old emitters, but the others are planning on new emitters to run it. You know, the new emitters will be chosen to run at 50 degrees flow or whatever. Mm-hmm. For just that old block, in the peak of winter, we'll need to bring it back up to, let's say, 70 degree flow.
Yep.
Using a water source heat pump in series, like you showed before, just for part of it, can they run with 50 degree input, do you know what I mean, on the primary side of it?
No, so what you would have to do, so the maximum absorption temperature for most water source heat pumps, I'll probably say all, to be honest, but I don't know, I don't make everyone's, but it's going to be about 35 to 40 degrees centigrade, and that's because there's only so much work you can do between the primary and secondary, and it creates some temperature issues as well, because the water source can accept temperatures down to like -5. So your maximum incoming is going to be about 35 degrees centigrade realistically. Mm-hmm. What you would do is you would have your air source heat pump for your heating load. You would have both of these sensors into different thermal storage vessels with different target temperatures, and then the zone which needed the higher temperature, you would pick up from the thermal store at 35. The zone that needed the lower temperature, you would pick up from whichever one you set to 50 degrees or 55 or whatever you wanted to do to satisfy the newer section of the building, if you see what I mean. And then the water source would literally just be dedicated to, it'd be a smaller water source, and it would be dedicated to the high temperature zone.
Yep, okay, that makes sense.
Cool. Awesome. Well, if you've got any more questions, or if you want to get schematics or whatever, just fire it through. I think it was Alex then, so and we'd be happy to take a look. That'd be cool.
Scott, can you hear me?
Yes.
Is everyone okay? That's great. I just wanted to reply to someone's question. I think someone requested or wanted to see if we can just provide afterwards the presentation, because it's been recorded. We can just ask for this and maybe email back to whoever wants to have it, if we are allowed. I don't know if we are, so I'm going to ask CIBSE, and whoever wants it, maybe he can include that to the email that you ask for them to send. Also, I would like to thank everybody for attending today, and you, Scott, of course, for the big opening. We were expecting to have, after the summer, we were expecting that we could be able to have face-to-face meetings, but apparently we're going to a second lockdown, so this is not going to be feasible. Hopefully you can attend us in the future. We have amazing events in the pipeline, including virtual tours and other CPDs. So yeah, thank you very much for joining, and yeah, see you soon. Thank you, Scott.
No problem. That's cool.